Hello students, welcome to lecture 8. In this lecture, we will introduce another algorithm called logistic regression. In the previous lecture, we studied linear regression. Right, and the linear regression algorithm can be used to answer the question related to how much, in our specific case was how much credit limit should be given to the applicant. It is a different problem than classification. We have seen that linear regression involves two-step learning, which is based on finding a matrix inversion or approximating pseudo-inverse of the matrix, which will give us the optimal linear regression weights. And we said that linear regression hypothesis uses squared error. And we derived the gradient of the squared error in order to minimize the in-sample error. Today, the outline of lecture is as follows. We first introduce the logistic regression problem, and then we will also introduce the logistic regression error function and the ways of how to minimize the logistic regression error, or by deriving the gradient of the logistic regression error function, and then using the algorithm called gradient descent that allows us to minimize the error of the logistic regression. Let us start with the following problem. Assume that we want to design a machine learning algorithm that will answer a question related to heart attack prediction. For instance, we have the following information from one patient: age, gender, blood pressure, cholesterol level, and then weight. Can we use classification algorithm for this kind of problems? The classification algorithm would provide usually the answer yes and no, which may not be the ideal case for this kind of problem, because there is no easy way to be certain for 100% that the patient will have a heart attack based on these features. So we need some softer decisions or hypotheses that will give us not yes and no answer, but some probabilistic answer. So if you recap our flowchart, we said that our unknown target function is a target distribution, P of y given x, which contains the ideal target plus noise in data. And this is our model, and we have our error measure, which we have added earlier. For linear regression, this error measure was the sum of squared error. For today's lecture, we'll derive a new error measure. So binary classification, given, assuming that our ideal target is a target distribution, will look like this. So it's a sign P of +1, let's say +1, probability of having heart attack. Given data, given the following data, -1/2 will allow us to generate plus or -1 based on the sign, right? If the probability of this event is higher than 0.5, then +1. If less than 0.5, then -1. Okay? This ideal function in this form will give us hard decision out, yes or no, right? So the softer version of this target function, which is based on the unknown target distribution, would be more appropriate. So if our target is again some probabilistic quantity that range between 0 and 1. In this case, we could answer to this question. The person may have heart attack with an 80% risk or 80% probability, which is softer than saying yes, he will have heart attack. So soft binary classification may involve softer decisions. Assuming that our target function is again the target distribution that involves probability density. Okay, the output range from 0 to 1. For the given all examples, data from patient 1, for example, 2, up to n, our hypothesis would give the range between 0 and 1. For example, 0.9, 90% of probability or risk that the data will be associated with heart attack, or probability of having heart attack given x2 is 0.2 or 0.6. And in this case, for example, probability of y given x1. So y could be plus or minus 1. Right? So ideal noiseless data, our target will always be correct. In actual noisy data, the output generated by the target function or hypothesis may be not accurate. For example, x1 will be labeled as the cross, and then red, and also red, for example. So giving us very accurate or hard decisions, +1 or 0. To solve this kind of problem that requires softer binary decisions, we can use a hypothesis, a class that is called logistic hypothesis. For example, again, for the following feature vector, which consists of the feature of the patient, we calculate the weighted risk score. Okay, this is S score, risk score, by applying weight to each individual features. And the next step would be converting this risk score to estimated probability by a logistic function called theta of S. The estimated probability will range between 0 and 1. The type of the functions we're interested now should allow us to estimate probability values, or can be linked with some probability when it comes to their outputs. So that range from 0 to 1. Okay, and let's call it as logistic hypothesis. Let's define the logistic function. One popular used function is called sigmoid function, okay, which is defined as follows. Theta of S is equal to exponential raised to the S 1 plus E exponential, right? Depending on the values of the S, which we define as score or risk score, we can plot the graph of this sigmoid function. If our risk score is too negative, okay, for sigmoid, then sigmoid will approximate the 0. And if we have our S to be 0, then 0.5, 1 over 2. And for high risk score values, if it is very high or even infinity, then the sigmoid function will reach +1. So we can interpret this sigmoid function as a probability. We can relate the output of this sigmoid function to probability values, depending on its argument, sigmoid, S, signal, or risk score. We can see that this function is smooth, monotonic, and the logistic regression use case will be the following. So h of x, 1 over 1 plus exponential negative w transpose x. We will use this type of function to approximate our target function. Okay, this target distribution. By the way, these two forms are equivalent. Just multiply numerator and numerator with 1 over es. Then you get the following form. And we define our hypothesis using this form. Now let's take a look at 3 linear models, 2 of which we have already studied. And let's call this as a linear scoring or linear scoring function of our input vector, input feature. So first, in linear classification, the type of the hypothesis function we considered were in the following form: h of x, sine, and then linear squares, where graphically we have different features, summing and passing some threshold function. And in this linear classification, we used 0-1 error function, especially in the perceptron case. Or how about the linear regression, which was the topic of the previous lecture? In linear regression, we don't apply any sine function. The output of linear regression is defined by just the linear square. h of x is equal to s. Graphically, we have again all the input features, just summing, passing through some identity multiplication. So this means that we're not doing any change. Our transfer, sometimes transfer function is identity. The output is following. And the type of the error function that we minimized for linear regression was squared error. Okay, the gradient of the squared error was easy to obtain, and minimization was also very easy, which involved one step. Okay, because the error function, squared error, is the convex of function also. How about logistic regression? We define our logistic regression so far as the theta function, which belongs to the class of sigmoid functions. Okay. Similarly, for the given linear scores, we pass through some transfer function which takes the sum and provides us the range between output range between 1 and 0. Now the question is, how can we minimize, or first derive the error function and minimize the error function for logistic regression case? So linear regression uses squared function, linear classification uses 0-1 error function. And how about logistic regression? Our next step would be defining this in-sample error or error function for the logistic regression. To derive logistic regression error function, first let's talk about the function itself, the target function itself. We said that the target function, the ideal target function, is actually the probability distribution. Probability of having heart attack in our case, given data. We can write this down for two cases. For example, probability of y given x. So y could be +1 or -1 for binary classification task, right? Assuming that the target function is f of x for all +1, then we can easily write it down as 1 minus f of x for all y's equal to -1. This is our target function. This is our target distribution that is generating our y's based on the data. Now let's consider a data set generated according to some unknown but fixed distribution, x1, and also we have the target distribution here. Each x input has its y's. We also assume each x is independently distributed. So we have the joint distribution of our data, defined by the probability that target function generated the data. So p of x1 and p of y given x1 times for all examples. Due to the independent assumption, we take the product. We can consider the other class possibilities just using the following, right? So 1 minus f of x2 will give us all possible points for -1 with the labels. In order to define the error function, we need to talk about the notion of likelihood. We said that y's, or the targets, are generated by some unknown probability or target distribution. We also have different hypotheses that we learn from the data. Our final goal remains same. We want to approximate our unknown target function using the hypothesis that we learn from the data. Now we ask the question, what is the likelihood that the A are the actual target that generate the data? Or what is the probability of data given hypothesis? By data, we mean the possible values for the y. If our h approximates the target function, then the likelihood of our h will be higher, will be also equivalent to probability of using f. And thus we want to maximize the likelihood. The likelihood of the hypothesis, they are actually the target that generate the data. Now the task is to maximize the likelihood of h, which will mean that we are maximizing the probability of using our target distribution. Okay, should be large. Okay, then we need to find the objective function that will allow us to select h with the maximum likelihood and declare it as our g. The likelihood of logistic hypothesis is defined as follows. Okay, we have seen that there are two cases for +1 and then -1. Let's make one change here. For example, 1 minus h of x2 can be written differently or simplified. One of the properties of the logistic function is as follows. So 1 minus h of x can be written as h of minus x. That can be easily checked in the sigmoid function we defined, theta. Okay, so using this property we can change 1 minus h of x2 to the following one by applying sine. H of x1, 1 minus h of x2 will change to h of negative x2. For all negative cases, we just applied sine. The sine can be defined by the y. Since we're dealing with a supervised learning task, we have y is either +1 or -1. So the input argument of our sigmoid or hypothesis or logistic regression hypothesis will have y's with each example. Given the function, let's call it as objective function, that's related to the likelihood of our hypothesis, logistic hypothesis, our next goal is to maximize it or to find the h that will maximize this objective function. This maximization will lead to so-called cross-entropy error function we will shortly reveal. So first, let's substitute our h with the sigmoid function. So basically maximizing is finding the weight of our hypothesis that will maximize this product term. There are a couple of the steps that we can do to simplify this product. First of the steps is just apply natural log on the product of this. Applying natural log on the products will be useful when the theta is very small number, the output of the theta. Now let's think about this objective. Can we change from maximization to the minimization? Yes, we just need to apply -1. While minimizing objective function is familiar to us because we've been doing that in perceptron or linear regression case, right? While here, maximization. So if we just apply -1 and do some changes to the product in the natural log case, we will have the following form. From maximization, we change into minimization. 1 over n, this is the average across all n examples. Now, the product of ln, this term, changes to the sum of individual natural log of those sigmoids. Now, let's define our sigmoid function. Okay, and then we have -s, 1 plus exponential raised to -s, and if you substitute here, we will obtain the following. Minimize the following objective function, minimize, find the w, that will minimize the following term. 1 over n, sum across all n examples. The negative goes inside the natural log, and then this one cancels out. We are left with 1 plus exponential, okay, negative yn w transpose xn. This is our new objective function that we want to minimize now. We can declare it as also our in-sample error function. Find the hypothesis with the following weights, logistic regression function. that will minimize our in-sample error. And this in-sample error is called as cross-entropy error. How we can minimize the following cross-entropy function, cross-entropy error? In linear regression, we found the W by matrix inversion, while in perceptron case, the 0-1 error function that we work with involved iterative nature. In this case as well, we can just take a look at the properties of this cross-entropy function. It's a continuous and differentiable, even twice differentiable function. Also a convex function. Okay, convex function, as I mentioned, have only one minimum. Only one minimum, that is the solution for this minimization problem. If our cross-entropy in-sample error function is differentiable, we can try to find the gradient of this function that will minimize or locate the valley where the gradient of this in-sample error is 0. Now let's think about deriving the gradient of our cross-entropy function. What we see here is that the error, in-sample error, consists of the natural log, exponential, and then the weight as an argument of exponential. We can take the partial or perform partial derivative of this function with respect to the weights. And here we need to utilize the chain rule for a composite error function like this. Here, partial of in-sample with respect to W will consist of 3 product terms. First, partial of natural log with respect to the arguments here, okay? And then we have partial of this term with respect to weights, and then we have also partial of this term, right? We know that derivative of our natural log is equal to 1 over its argument. Derivative of this term will be equal to exponential, and then the following. The derivative of the following term will be equal to y x n negative, where w is 1. So we can further simplify the following terms and have the following. So 1 over n, sigmoid function. Okay, this is sigmoid, exponential 1 plus exponential of the following, multiplier y and our x input. So the gradient of cross-entropy function is equal to the following. How we can minimize the derived gradient? At an optimal, the gradient of our in-sample error should be 0. That represents a minimum of our in-sample error, right? Here. If you take a closer look at this gradient, we see that it is the sum of a weighted sum of all examples, which is scaled by the following term, negative y and xn. Right? Now, can we solve for w and obtain the optimal weights as we did in the linear regression problem? No, because the sigmoid is a nonlinear function, therefore it will be difficult to solve for w. We don't have any analytic solution for this gradient function for this problem. Okay, so we can also see that theta, the sigmoid, will be 0 if it is very much a higher number, greater than 0. This may happen for linearly separable data. How about the weight? As I said, this is a nonlinear equation, so we can solve for the w. Let's revisit the perceptron learning algorithm and how we did an iterative optimization step there. The PLA starts with some random weight and tries to update the weight if it makes a mistake on a given example in a data set. It involved 2 steps for a predefined trial, so iterations. Find a mistake of the current weight on any example which is represented by the following. If the sign of the weight and then given example doesn't agree with the given label or target value, then it made a mistake. Then move to the second. Then try to update the weight by the following update rule. So the new updated weight will be t plus 1 of the current weight plus an example, okay, that it made a mistake. And we have y scalar. So let's combine these 1 and 2 into one update rule. So this is equivalent. So the new weight, update weight, is equal to current weight plus the update term, right? The current weight will be updated if this boolean function is true, then add this current point. Combining the first and second step in the original perceptron algorithm, we have now only one step. We can introduce some parameters here, such as eta, the v, or we can also define it as a vector, because this is what we have, the x input vector. So y is scalar. The output of this is either true or false, 0 or 1. We can also change the behavior of this optimization step by changing eta and v. Let's try to think about the role of eta and then v in an iterative optimization problem. In PLA, the v vector comes from mistake correction. How about logistic regression or our cross-entropy function? Can we apply or adopt similar iterative optimization in minimizing the error function? Yes, the in-sample error in logistic regression or the cross-entropy is a convex function. Find the direction of the gradient that will bring us down the hill to the minimum, and we can relate that gradient vector to the v and update the current weight. In other words, we need to choose the direction where the v will take us to the downhill. For a fixed step size, eta, we can use grid approach in finding the direction to the downhill, which will bring us to the minimum of the cross-entropy function. So the greedy approach is based on finding the local best direction that leads to the minimum step by step in an iterative manner. The grid approach is now a nonlinear optimization with the constraints now. We want to move one unit vector length direction at a time. We can try to approximate this in-sample error using Taylor expansion, using a local approximation by a linear formula, which can make the problem easier. Then the approximate greedy approach for some small eta will be equal to the following. So we have minimize the in-sample error subject to the length of the vector is equal to 1, given some positive eta learning rate, and vector, this is our gradient. What we know about here is that the in-sample is known, in-sample error for the given weight can be calculated, and eta is user-defined parameter, usually some small positive number. V, okay, V needs to be defined as the opposite direction of the gradient, and the gradient also known for the given weight. So what we need to do now is that to make the V the unit vector, we can normalize. V, we can relate to V as the direction of the gradient by a length of 1, unit direction, right? So we normalize by the norm of the gradient. And the opposite direction is defined by the negative here. We can now define finally the learning update rule. So it's based on updating the weight, the current weight minus eta, and the opposite direction of our gradient. Well, now we can think about the different values of eta, the learning rate, and how it affects the obtaining the minimum of the area function. Gradient descent is a very popular and simple optimization technique that is used in minimizing some sort of cost or error function. So we have different options regarding the choice of eta in the weight update. If you set it to too small in updating the weight, and that will take to the minimum will be very small. Eventually the minimum will be found, but it will take time for the optimizer to reach this minimum. If you set too large eta, then we have this kind of zigzag, unstable situation. Well, the just right or the correct eta that is suggested is to start with smaller learning rate or step size and then minimize. Okay, this is an adaptive learning rate. Or it's even better to relate the eta to be the monotonic of the norm of the grade. Let's put everything together and summarize the logistic regression algorithm. So first we initialize weights and we define the number of trials. Step 1, we compute the gradient of the cross-entropy function using the current weight and for the given example. And depending on the size of the gradient, we apply the weight update. Basically, the weight update is based on this. the new weight is based on current weight minus this term. The gradient is calculated in step 1. If the gradient is 0, then update will not happen. And also we have introduced some user-defined parameter which is called step size or learning rate. And this should be set more adaptive, in an adaptive way, done until the gradient of the updated weight eventually, this one, will be 0, or until enough iterations if you cannot reach 0. And return this as the last G. To summarize this lecture, we have studied the algorithm or class of functions called logistic regression, which can be used for estimating probabilistic outcomes. So we have talked about a hard fate prediction problem as an example. The output of the logistic regression can be interpreted as genuine probability values. We defined logistic regression error, which was based on maximizing originally the likelihood. From maximization, we changed to minimization of the likelihood and applied negative log likelihood and derived cross entropy. After that, we derived the gradient of the cross entropy and came up with the gradient descent or weight update rule based on the gradient descent.